I'm Misaki Komatsu from Toshiba, Japan. The title of this talk is Semantic Definition of Anonymity and Identity-Based Encryption and its relation to Indistinguishability-Based definition. This is a joint work with Goichiro Hanaoka, Kazuma Ohara, Yusuke Sakai, and Shota Yamada, who are all from IBES, Japan. It is necessary to establish of some basis whether a cryptographic protocol is secure or insecure. When you hear all this, it might sound that there is an absolute standard and all cryptographic protocols are divided into secure or insecure according to that standard. However, the reality is a bit more complicated. Cryptographic need to make it clear on mathematical and other grounds whether it is secure or not. However, cryptographic security is not something can be separated into secure or insecure. This is because when we think about the security of cryptography, we give a security definition that captures certain security intuition and then make a formal decision on whether the definition is met or not. In other words, whether this definition of security correctly captures the required security is another matter. After defining security, we have to make sure that it is indeed met. Let me give you a concrete example of this story. Here, we would like to look at an example on the relationship between the security and the definitions in the context of public key encryption. What we want to prove is that ciphertext leaks no information about the plain text. To capture this security, Goldwasser and Mikari introduced the notion of semantic security. Although the definition is not straightforward to prove the security, however, Lelazé shows that semantic security is equivalent to indistinguishability notion, which is better facilitates proving the security in practice. In many cases, SS-based and IND-based definitions achieve equivalent security. However, we note that it is possible for IND-based and SS-based definitions not to be equivalent, which is evidenced by some separations result between IND-based and SS-based definitions in various cryptographic primitives and notions, such as functional encryptions. Let's study detail with the security notion of identity-based encryption. First, we give a brief explanation of the IBE. IBE is a kind of public key crypto systems consisting of 4 probabilistic algorithms. The key properties of IBE are that a user can generate a public key from a non-unique identifier, such as an email address, and a trusted third party can generate corresponding private key from the public key. We can classify the security for IBE into 2 categories based on what information is assumed not to be read from ciphertext. One is plain text sequence, which refers to plain text information. The other is anonymity, which refers to identity information. An IBE that satisfies anonymity is called an IBE. There are also cryptographic methods that use the property of an IBE, such as searchable encryption. In this time, we will focus on the anonymity notion of IBEs. Searchable encryption allows to search a piece of information over an encrypted data, while keeping the data contents and the query secret even from the server holding the encrypted data. In particular, one of well-known constructions for searchable encryption in public key setting is based on anonymous IBE, and the secrecy of the secret search queries impacts relies on the anonymity of the IBE. Several definitions of IBE anonymity have been proposed. However, all of them are IND-based definitions. In the presentation, we used the IBE notion to simplify this discussion. IBCam when combined with the appropriate symmetric key cipher result in an IBE. So, what we were doing is pretty much the same. This slide shows Ano-LOR, which is an IND-based anonymity definition. Ano-LOR is formulated as a game between a probabilistic polynomial time adversary and the challenger. The adversary chooses two IDs and tries to guess which one was encrypted when he receives one of them encrypted. An IBCam scheme sigma is Ano-LOR secure if it is impossible to identify which IBE is used. As explained, the IND-based definition of anonymity already exists. However, as with other cryptographic protocols, it is unclear whether the definition captures semantic security. An important overlooked issue is that previous studies have not given an SS-based definition of IBE anonymity. Then, unlike with PKE, we don't even know if SS and LOR are equivalent. So the question here is that, do the existing IND-based definitions really capture what we want to capture? For this purpose in this work, we define semantic security type definition of anonymity for identity-based encryption. This may better capture the intuition that many information of the identity is leaked from the associating ciphertext. Here, I explain our first attempt to define semantic security for anonymity of identity-based encryption. To give the definition, we consider two types of the word, real world and ideal world. In the real world, a ciphertext is given to the adversary. On the other hand, in the ideal world, the adversary is not given honestly generated ciphertext. Instead, it is given a simulated ciphertext that is created by a simulator who does not know the associating identity. If these two are computational indistinguishable, we can say that the information of identity is not leaked from the ciphertext. One may think that it may be straightforward to give semantic security style definition for the anonymity of IBE by following the approach of Goldwasser and Misaki, who gave the semantic security for public key encryption. However, it is not the case due to the existence of the key generation oracle. Rather than using Goldwasser-Misaki style of definition, we adopt alternative approach for defining SS anonymity. In particular, we specialize the semantic security style definition of anonymity given by we, for more generalized primitive of attribute-based encryption to the special case of IBCam. The definition is simulation-based, which requires the real and the simulated world are indistinguishable. We then explain the definition of the real game played by the adversary. In the real game, the step-up algorithm is run, and the public parameter PRM is given to the adversary. Then, the adversary chooses its target identity ID primes, and is given the ciphertext and the key corresponding to ID prime. During the game, the adversary is equipped with key generation oracle that takes as an identity ID and returns secret key for ID. We restrict the adversary from making a key query from the challenge identity ID prime. We then define the ideal world. In the ideal world, set up encryption and key generation algorithm and replaced by simulated one. The critical difference from the real world is that the simulated encryption algorithm does not take the identity as input. This captures the idea that the ciphertext does not reveal the information of associating identity. We define the scheme to be secure if we can construct simulated version of the algorithm, set up, keygen, and encryption, so that the real and ideal world are indistinguishable. Since the simulated encryption algorithm does not take the target identity chosen by the adversary as input, if these two worlds are indistinguishable, this suggests that the ciphertext indeed does not leak any information of the identity. To validate our SS style security definition, we first show that the SS definition of anonymity implies Ano-LOR. This is proven by constructing SS adversary from Ano-LOR adversary. Here, we only explain key points of the proof, and refer to the paper for the full details. In the proof, the SS adversary A will handle the queries made by B by using its oracles. When B makes the encryption query for two identities, B chooses random one from the two, and then submits its encryption oracle. Then, B passes what is given from the encryption oracle to A. The most subtle part of the proof is how to answer the key query made by the LOR adversary B. In particular, we have to make sure that A does not make any key query. Thus, that is prohibited by the game when answering B's key queries. This can be done without a problem, because the restriction on key query for B is stricter than that for A. In particular, while B is allowed to make a key query from any identity except for the two target identities it chooses, A is allowed to make a query except for signal identity, which is randomly chosen from the two identities B submitted. We defined Ano-SS, which is a more intuition definition of anonymity for IBE, and proven that Ano-SS implies Ano-LOR. We want to prove that the other direction, namely Ano-LOR implies Ano-SS, so proving Ano-SS and Ano-LOR. To do that, we can use the standard technique of game hopping. While the changing from game 0 to game 3 are standard, the change from game 3 to game 4 is a bit complicated. Let me elaborate on this game hop. The change from game 3 to game 4 is the rejection rule of the key generation oracle. In game 3, the oracle returns both when ID 0 and ID 1 are queried. In contrast, in game 4, the oracle returns both only when ID 1 is queried. If the adversary can't know ID 1, the gap between the games is negligible. However, ID 1 is encrypted in a ciphertext city as the identity, and this city is given to the adversary. So, to ensure that the adversary doesn't know ID 1, we need the anonymity of the IBE scheme. In other words, we need anonymity to prove anonymity. Let me summarize the situation. We need anonymity to prove anonymity. However, what we want to prove is Ano-SS. What we've assumed is Ano-LOR. So, the assumption of Ano-LOR may help proving Ano-SS. But unfortunately, we can't directly apply Ano-LOR to the current situation. To make Ano-LOR applicable, we introduce intermediate games between Game 3 and Game 4. These are the intermediate games. In Game 3, the adversary can obtain the ciphertext of ID 1. In the Game 3-1, the oracle returns both when the randomly chosen identity ID 2 is queried. In Game 3-2, the ciphertext city is challenged to the ciphertext of ID 2. In the final Game 3-2, the information on ID 1 is completely hidden from the adversary. So, Game 3-2, the adversary can't query ID1. Furthermore, the gaps between these games are negligible. Also, in Game 3, the adversary can't query ID1. This is a summary of the game sequence. Game 1, 2, and 3 are standard, but the game hop from Game 3 and Game 4 is slightly complicated. We overcome this complicated situation by introducing intermediate game Game 3-1 and Game 3-2. Finally, we prove that the real and ideal game is the Ano-LOR have a negligible gap. It implies that Ano-LOR security implies Ano-SS security. I conclude this talk by mentioning some suggestions for our equivalence result. First, for the first time, we proved that Ano-SS and Ano-LOR are equivalent. This implies that all the existing IBE schemes secure under the Ano-LOR definition is secure under the Ano-SS definition. So, from now on, it is enough to use Ano-LOR definition for security proofs. This fact not only guarantees the security of the IBE scheme proven security under the IND-based definition, does it allow us to keep using the easy-to-use IND-based definition as we did. Finally, our proof suggests that the standard technique of gold-washer mimicry is not always applicable. This further suggests that the equivalence between IND-based definition and SS-based definition is not always true. This observation encourages us to carefully study the equivalence between IND-based and SS-based definitions for more sophisticated primitives, such in equivalence already occurred in functional encryption. This ends my talk. Thank you for attention.